So we've talked about some of our different routing protocol major classifications, such as our distance vector, our link state, and our hybrid. But what is our IGP versus EGP? Well, we have another classification that we break down our routing protocols into, and this is an interior gateway protocol or an exterior gateway protocol. IGP, interior gateway, and EGP, exterior gateway. IGP protocols, IGP routing protocols, are protocols which work inside an autonomous network, which means they work inside a network which is singly managed and singly connected with all of our different routers. So the internet is not an autonomous network. We aren't using RIP or RIP-v2 or OSPF in order to connect all the routers across the world, across the internet. That's not the way that works. But if we have, say, a large enterprise building or a large government building or a office building that we're using and trying to get multiple different routers to communicate with each other, then those routers are communicating and those routers are setting up their routing tables using an IGP, using an interior gateway protocol. We think interior, we think of we think of internal networks rather than external giant public networks. Now, EGP, exterior gateway protocol, is connecting out to the internet, is connecting out multiple large giant networks together. And our EGP protocols, our exterior gateway protocols, there's only one that we use, and this is Border Gateway Protocol, BGP. Whereas IGP uses RIP, RIP-v2, OSPF, IGRP, or EGRP, Exterior Gateway Protocol only uses BGP, only uses Border Gateway Protocol. So what is Border Gateway Protocol? Border Gateway Protocol is a path vector protocol, and path vector, you guys haven't heard of it yet because I haven't mentioned it yet. Well, you haven't heard of it yet in this video segment. Path vector protocol is similar to our distance vector, which we mentioned. Our distance vector is where we measured based on hops between different routers. Path vector is similar to distance vector, except we only have one speaker node per domain of routers. So think of it this way. If our border gateway protocol needed to talk to every single router in the world in order to determine the paths, it would be very, very difficult for that border gateway protocol to ever come to any sort of conclusion as to what was the best path. But with our border gateway protocol, if we have our router here, and this router is going to try to talk to other routers in order to get information on what their routing tables look like and what information is different metrics that they're trying to use. If we have one router, so we have our one main router here that connects to all the other routers back in our domain, and then over out on the internet we're connecting to a domain which has one main router which connects to multiple different routers. Rather than all of the routers across our border gateway protocol talking to each other, in each of our domains we choose one speaker node. We choose one representative. Think of each state chooses their senators. Each domain chooses its speaker node. So we choose our one main speaker node per domain to talk to the other speaker nodes. So this greatly reduces on the traffic that we're sending out over the exterior. This can help us to manage what kind of information we're sending out over the exterior, because our different routing protocols not only transmit different metric information, but they also transmit routing tables. They let other routers know, okay, hey, these are the routing tables I've got, let me see the routing tables that you've got. And if we have our network connected to the internet, we don't necessarily want everyone on the internet to be able to see our routing tables. Well, why not? What's the harm? Well, there could be potentially a lot of harm. One layer in all of our different security layers is layer by obscurity. Now, this is not the best layer of security. It's not the strongest layer of security, but it is a still very viable additional layer of security to tack onto all of our layers. What security by obscurity means, other than just rhyming, means that we are helping secure our networks by not broadcasting out to everybody what's inside our network. It's harder for attackers, and it takes more time for attackers to be able to do what's called enumerating our network. And when they enumerate our network, they find what's in our network. If we don't broadcast out, hey, here's my routing tables that list what servers I have on my network, what this name server, how you get there, and what routers you need to go through in order to get to my workstations and to get to my web server and to get to this and that and the other. Because remember, our routing tables are going to include information such as our different IP addresses and subnet masks and a lot of information that we just may not want computers outside of our network, outside of our organization to know. So we can limit that by limiting what information is being broadcasted out from the speaker node for our domain on our border gateway protocol. So again, IGP, Interior Gateway Protocol, is going to be inside our autonomous network, which is going to be all of our protocols we have over here on our left. And EGP, our Exterior Gateway Protocol, is going to be connecting to our external networks and routers, and it's going to utilize BGP, Border Gateway Protocol. And Border Gateway Protocol is the only exterior gateway protocol that we use. And Border Gateway Protocol is a path vector protocol, which means it's similar to a distance vector, except we only have one speaker node for domains. Now we have all of our IGP protocols, all of our interior gateway protocols. These are different protocols that our routers are going to be using in our environment. All of our different routers on all of our different floors and offices across our building, across our domain, are going to be using in order to communicate with each other, in order to exchange routing table information and exchange different vector path information and exchange speeds and latency and all that. They're going to use an IGP, an Interior Gateway Protocol. We have 5 Interior Gateway Protocols listed up here. RIP, RIP version 2, OSPF, IGRP, and eIGRP. Don't confuse IGRP with IGP or eIGRP with EGP or IGP. IGRP is just one of the 5 protocols. It's not an additional. It's not an additional. It's not like an additional type of protocol or anything like that. Just because it has IGRP. So know the difference between IGP and IGRP. So RIP stands for Routing Information Protocol. RIP is a distance vector protocol, which means it's based on hop count. But RIP has a lot of limitations. Our routers that are using RIP in order to communicate and in order to determine which routes they should take can handle no more than 15 hops, which in a small network with a couple routers isn't a big deal, but in a larger network with a lot more routers is a big deal. So our routers that are communicating and that are finding paths using RIP are going to be using just hop count in their analysis. We'll set static routes, but their dynamic routes are just going to be hop counts, because remember, all of our protocols we're talking about right now are dynamic routing table protocols, are protocols which are used in order to update our dynamic tables on our routers. So RIP is only going to utilize hop count, but it's not going to be able to handle routes with more than 15 hops. It's also not going to allow us to use classless IP addressing. It's not going to be able to handle what we refer to as subnetting. So if we're trying to set up classless IP addressing, if we're trying to set up different subnets on our network, RIP routers which are using RIP aren't going to be able to handle that. They can't handle classless addressing. They can only handle class-full addressing, which is our standard Class A 255.0, which is our standard subnets, Class A 255.0.0.0, Class B 255.255.0.0, and Class C 255.255.255.0. Essentially, our RIP protocol just looks at the IP address and says, oh, this IP address has a default subnet mask of this, so that's what it's going to be. It doesn't take a look at this. It doesn't need to take a look at the subnet mask. It doesn't take a look at the CIDR notation. It just says, oh, this IP address needs this subnet mask. I'm going to apply that, and I'm going to look for networks. I'm going to look for routers which manage that. So if we're trying to set up classless addressing, it's not going to work in this environment where we're just using RIP. So we have RIP v2, Routing Information Protocol version 2, which goes in to address some of these issues. Now, RIP version 2 is still a distance vector protocol, which means it's still just using hop counts, so still a little bit weak. RIP v2, however, has support for more hops, so it gives us significantly more hops than 15 as our limit, and it will also give us support for classless addressing. So it'll take a look at that subnet mask and say, wait, this isn't a default subnet mask, so this must mean that we're trying to do some subnetting here. So RIP v2, if you're using one of the RIPs, then you want it to be the RIP. If you have to use one of the routing information protocols, you want it to be the RIP v2, because RIP v2 is going to give you support for more hops and support for classless addresses. Then we have OSPF. OSPF stands for Open Shortest Path First. Now, OSPF is the most commonly used interior gateway protocol. It's the most common protocol that you'll find on routers, them using it to find different routes across networks. So remember, OSPF, Open Shortest Path First, it's the most commonly used interior gateway protocol, IGP, for finding routes and setting up routing tables on dynamic routing tables. OSPF uses link state analysis. Remember, we mentioned that link state analysis is cost-based. Checks out things such as how long it's taking to get from one location to another, the round trip time. It checks out things like the bandwidth or MTU. It's using that cost-based analysis of, okay, if I'm going to send this packet from my location to this location using this route, what's the cost of that? Is that going to be a lower cost, a lower round trip time, a better connection back to me, which is a lower cost, which is good, or is it going to be a higher cost, which is bad, which is a bad route for me to use? I said bad multiple times there. So high cost is bad, low cost is good. So that's what link state analysis is. We talked about that earlier, though. Link state analysis is what is going to be used by Open Shortest Path First, OSPF, our most commonly used interior gateway protocol. And then lastly, we have, last two, we have IGRP and eIGRP. IGRP and eIGRP are both Cisco. So these will be on Cisco routers. They are Cisco protocols, so you'll see them there. IGRP stands for Interior Gateway Routing Protocol. So don't get it confused with standard IGP. IGP, Interior Gateway Protocol, contains all of these other protocols. So IGRP is a Cisco distance vector protocol, which means, again, distance vector, just like RIP and RIP v2, is hop-based. However, IGRP has can handle more hops than RIP, but it's still no classless. So it can't handle classless addresses. Forgot to mention, OSPF it does handle classless addresses, so it can handle subnetting. IGRP cannot, and RIP cannot handle classless addresses. But IGRP can handle more hops than RIP can. And then, just like RIP needed something to fix this problem with not handling classless addresses, we released eIGRP, which is Enhanced Interior Gateway Routing Protocol, Enhanced IGRP. This is a Cisco hybrid protocol, which means that we have our enhancements to IGRP in that it not only uses hop counts, but it also uses link state analysis. So it also uses cost-based analysis, and it uses a combination of hop count and cost to each link in order to determine which routes are the best. So our eIGRP is also going to be able to support classless. Yay! So that's going to be our 5 routing protocols. RIP, routing information protocol, distance vector, no more than 15 hops, no classless. RIP v2, more hops than RIP 1 and has support for classless, still of distance vector. OSPF, open shortest path first, is going to be the most used IGP. Link state analysis, so is cost-based. IGRP and EIGRP are both Cisco, interior gateway routing protocol, enhanced interior gateway routing protocol. IGRP is a distance vector, does not handle classless. EIGRP is a hybrid, and it does handle classless. So, using our knowledge now of our IGP versus our EGP, we're able to recognize how we make our distinction between our interior gateway routing protocols. Our interior gateway routing protocols being, again, in all the routers inside of our network. And then EGP, exterior gateway protocol, being our networks connecting out to all of the different internet, different domains, all those different networks out there. EGP utilizes BGP, Border Gateway Protocol, in which each domain chooses a speaker node. One speaker node per domain. And IGP contains all of these different several protocols which we talked about. So hopefully you'll be able to take these, and we'll be able to pick the best routing protocol for our routers, and we'll be able to find out we're able to understand more about how our routers actually find their paths using these different protocols.